I'm going to give a short intro talk on namespace-focused APIs introduced by the NDN-CNL from our team, and then there'll be a longer talk on a specific realization with some practical examples. So if you look at the NDN library list that Alex showed, this is more or less kind of also following a timeline, though we don't go all the way back to the CCNX libraries. So the original CCNX APIs were focused on forming the wire format, forming packets and sending them across the network, though there was some early work on content object and utility abstractions. That was followed by NDN-CCL and CXX libraries that focused on intrastate exchange, abstracted away from the packet format details, and integrated work on schematized trust, access control, and so on, that were all built basically at the level of intrastate exchange. And a lot of the early apps were using those APIs. And as Alex mentioned, and Len has already shown, we want to move away from that. There are also some descendants that use modern language features such as NDN-TS for TypeScript, for example. And there was some work also on higher level fetching and publishing patterns and pub/sub libraries that you've seen even recently, which are a natural extension to NDN, kind of treating name prefixes as topics and providing the scaffolding to think of them in terms of pub/sub. And then most recently, or in parallel with the emergence of these pub/sub approaches, was the NDN-CNL, which is an attempt to organize the asynchronous networking that an app has to do in NDN and really in most modern applications via the namespace itself. And we're going to look, I'll briefly introduce that and some of the motivations, then we'll look in more detail at a specific realization that by simplifying a few things also makes it pretty easy to put applications together quickly in Python. So the overall objectives for the namespace-based APIs is to try to make an attempt to align app design with name data design right without focusing on intrastate mechanics, compose those various data-centric approaches that if you look at the example on the right, you can see versioning is handled at one level and the hierarchy segmentation at another. And as you go up, you get closer and closer to something that looks like a name for a typical application object. And at various places in this hierarchy, you might be essentially applying either a naming pattern, some type of serialization or deserialization to generate a child hierarchy and so on. But we want to be able to, rather than having to hand code how those elements work together, start composing them by attaching them into a namespace representation. And one of our other objectives was to incorporate sync as a first-class capability, basically to really force us to think about multi-party communications on those namespaces. So in ICN last year, we presented the NDN-CNL, which was really, to me, the first realization of a concept, not necessarily our last attempt. It focuses on an in-memory namespace representation that's maintained by the library on behalf of the application. So this is really just an extension to the notion of a memory cache that many of the libraries provide, where there's some in-memory cache of objects. We happen to allow access to the typically hierarchical organization of that namespace in the API. And it also aims to try to provide the ability to manipulate app-level objects associated with prefixes all the way down to data packets and provide some symmetry even between producers and consumers, who, if you think about it, producers and consumers at some point learn about names either from themselves or from others, and either create or receive data associated with those names. But there's a fair amount of symmetry in first they have a knowledge of a name, and then they either create or consume the data associated with it. CNL allows the attachment of handlers to the subtrees in the namespace that take care of the mechanics of that. Our other goal was to try to stick with a small set of features and minimize the loss of generality relative to the existing common client libraries that the CNL is based on, and also without making a lot of assumptions about the form of the namespace. By focusing the namespace constraints and making a few other design decisions, NTSchema can simplify things significantly, trading off some of that generality. So what does this look like in a specific example? So if we imagine a namespace, a high-level namespace foo that contains images from an application's perspective, at a high level, that application might not actually think about the name as representing an immutable piece of data or set of data on the network, but rather a mutable image object that has different versions represented in the next level of the hierarchy. Of course, the names at that level are starting to represent immutable versions of that image, if you think about the NDN format. And then, of course, at a lower level, when you get down to the packet, you might have individual segments. And we want to be able to attach abstractions in the CNL to various levels of this, so as I sort of described before. The other assumption or goal was to focus on multi-party communication with sync. And so generally TCP is providing a two-party transport abstraction on top of IP. And in NDN, we have this capability to start thinking about multi-party communications as the norm. And what are those communications about? They're about the contents of the namespace. And so no matter who's publishing objects within that namespace, the goal of the CNL is to propagate information up to some depth about the available objects in the namespace, and not necessarily force an application to fetch them, but to at least know what objects are available in namespaces of concern. So there are other ways to think about this. If you know the namespace in advance, you don't need to necessarily run sync. But in this particular case, the CNL is sort of imagining various instances of the application are communicating via sync. When new names appear, regardless of who publishes them, as long as they're participating in the synchronization, then you can follow a specifically attached handler for each name to decide what to do to fetch it or so on. And by keeping the namespace in memory and synchronizing across different instances, we're able to make some trade-offs. Of course, it takes more memory. There's more resources required to do this for large namespaces, and some optimization challenges as things get larger. But it also allows us to do things like enumeration, search, regular expressions, and so on against the namespace because we have that local representation. I should clarify that when I'm talking about sync here, I'm not necessarily talking about using pub sub on a prefix. In particular, that might be a specific handler attached to a prefix. Here I'm talking about a more general use of sync within the library to maintain a picture of a high level or general prefix that may or may not really be following a pub sub paradigm. So if you dig further into the library implementation, a lot of the initial examples are around what we're calling generalized objects. So these are objects that have a standard metadata and manifest approach that can then be collected into a sequence that has its own additional metadata and follows the real-time data retrieval protocol that I think was published on a couple of years ago to allow us to get what essentially is a real-time stream of these objects. And so this is an example of something that the CNL can abstract at the stream level and present to us, allowing applications, for example, to manipulate that prefix or any intermediate child depending on what it is that they actually need. So for example, if the app wants to attach, in the ideal scenario, this isn't, I don't think this is realized right now, but if an application wanted to, for example, attach the RDR protocol to the stream or an RDR protocol handler, it would point it to the stream prefix. Because it has the appropriate naming conventions for the latest data, that protocol would work in the kind of expected manner. And then each of the individual objects, the generalized objects, when they are retrieved from the network, can be provided to the application in an object abstraction that makes sense for the application to use based on the interpretation of that namespace. So a couple of the sort of complexities here are, of course, somehow the application has to know what schema is attached to a name. And in the NTSchema example, you'll see at the end, with those known in advance, things get a lot simpler. If we want to try to dynamically detect the presence of schema, we still have to make some assumptions about how metadata objects are named, and so on. And so I think, again, as I mentioned, we're sort of making as many generalizations as we can, and then trying to figure out, well, where are the pain points in terms of operationalizing this in a real application. And one of them is to know what schema is associated with what aspect of the namespace. And so far we're doing that based on some a priori knowledge in the application, but would expect that it could be published in metadata in the future. So a quick producer-consumer example that are a lot like what Lan showed. After initializing the application, you might specify, create a namespace, which is the in-memory representation, and attach to it an object handler. Then add the objects as you have new elements of the stream, and that's it. And so what's happening on the back end is that those are going into a cache in memory. If there are other instances of the application, the names that correspond to those objects as you look back down the tree are being synchronized up to some level, and probably just up to the prefix level in a common application. And then the RDR protocol can be used by consuming applications to retrieve those new objects. And so on the other side, we would attach the handler and make a call to the function object needed. And this is trying to provide some symmetry between the producer and consumer. So it's the same handler. It specifies that it needs the object rather than has the object. And then when it's retrieved, processes it in a simple way as is shown here. And so I think what we've seen, so we've tried to pull this way of working with namespaces into other libraries and applications. So this is just a screenshot from a real-time media processing language. And we've found that it has helped us to move away from dealing with interest data exchange. But one of the sort of significant challenges is that by, again, working with arbitrarily structured namespaces, we need some way of formalizing and schematizing the namespace, the fetching patterns and handlers that should be used for a given namespace. It's easier to kind of describe the composability than to implement it when there are different interactions across the components. So the library implements a common state machine that does signing, encryption, versioning, segmenting, and those types of operations in the same order, and provides some structure and some predictability for what composability means. But when you're looking at applying things in multiple overlapping places in the hierarchy, this gets sort of complicated. And so though we have done some applications with it, I think what's interesting in what will be presented next is the attempt to make some simplifications and get a much easier to use application API as a result. And so I think what's happening in this, sorry about that. I think what's happening in this particular case is we might start to see a continuum of different namespace approaches that focus on allowing applications to manipulate namespaces, but with varying levels of constraint on the structure of those namespaces, or very hopefully soon some type of standardized metadata to interpret what type of objects are associated with what prefixes. So with that, I'll turn it over to the next speaker to go into a specific example of NTSchema.